Let me run you through a couple examples of calculating torques, and we're going to do it two different ways. We're going to calculate using the cross product, and then we'll calculate using the scalar equation. So let's just take a fairly simple situation. Let's say that we have a lever, and just for simplicity, I'm going to go ahead and place that lever at 45 degrees there, and then let's apply the force in the upward direction, and let's apply a force of 20 newtons, and we'll have a lever arm with a length of 0.3 meters. Now, if I'm going to use the cross product to calculate this, I'm going to need to write my vectors out longhand. So my r vector then is going to be equal to the magnitude times the unit vector. So the magnitude is 0.03 meters. The unit vector now, let's see, with respect to the x-axis, we have cosine of, that's got to be 135. And then the cosine with respect to the y-axis is cosine 45. And then with respect to the z-axis is 0. And let me just draw in my axes just to be really clear here. So positive x is to the right, positive y is up, which means that positive z is coming out. That represents an arrow with a little tip coming out. So the next thing to do is to write out the force equation. So that's going to be equal to, we put it in the positive y direction. So the magnitude is 20 newtons, the unit vector is 0, 1, 0. Now, if I actually calculate these out, cosine 135 is going to give me a negative 0.707. Cos 45 gives me a positive 0.707. So my r vector comes out to be 0.3 meters times negative 0.707, 0.707, 0. And that kind of jives with what we have going on here, because the lever has a negative x component to its extent. In other words, it's pointing in the negative x direction, but in the positive y direction. And so this vector kind of lines up with that. Now, to calculate the torque, you actually have the equation for the cross product on the equation sheet, and I do recommend that you take a look at that so you're comfortable with it. So the cross product is going to be r sub y f sub z minus r sub z f sub y. And one thing to notice is that to find the term that you subtract, all you do is you switch the first two subscripts. So the next component is going to be r sub z f sub x, and then just based on this, I know that the next component is going to be the same thing with the subscripts flipped, r sub x f sub z, and then finally r sub x f sub y minus r sub y f sub x. Well, another thing to notice is that the y component of torque the x component of torque doesn't contain the x component of r or f. The y component of the torque doesn't contain the y component of r or f, and the z component of these two objects, these two vectors, does not appear in the z component of the cross product. And that's because cross product is really dealing with perpendicular components. So let's go ahead and take a look at what we get. Notice that r sub z is 0, as is f sub z. So these term and these term right here are both going to be 0. I'm also going to run into the same problem here. R sub z and f sub z are both 0. So these first two components end up being 0. Now, if we take a look at this right here, r sub x is, let's see, negative 0.707 times 0.3 meters times the y component, a force, which is just 20 newtons. And then looking at this term right here, r sub y would give me 0.707, but f sub x is 0. So we're just left with this right here. And calculating that, we find 4.02 is what this term gives us. So the torque is equal to 0, 0, 4.2 negative Newton meters. So let's just check and see if this makes sense with what we'd expect. So get your right hand and starting at the pivot point, place your fingers so that they're pointing along the beam, and then curl your fingers up in the direction of F. And if you did this, you should see that your thumb is pointing into the screen. You notice that positive Z would be coming out, so going in is negative Z. Sure enough, we have a negative Z component here. So that agrees with what we would expect. Now let's try the scalar method. The scalar method tends to be a little bit easier. The only thing is you then have to insert the direction of the torque manually. So the magnitude of torque is equal to the magnitude of R times the magnitude of F times sine theta. So let's go back up here, and the angle that we're actually concerned with is, so drawing a line out from the pivot point, and then actually I should have placed the tail of the force here. So let's just ignore this one for a minute, and this is the force vector. Then the angle that I'm interested in is this angle right here, which turns out to be 45 degrees. So going down here, we get R is equal to 0.3 meters. The force is 20 newtons. Sine of 45, and sine of 45 is 0.707. So we get 0.3 meters times 20 newtons times 0.707. So the magnitude of the torque is equal to 4.2 Newton meters. Now that we have that magnitude, it's up to us to see if we can figure out which direction it is. This is where the right-hand rule comes in handy. And so using that right-hand rule, you see, aha, this has to be in the negative y direction. And so from that, you can then draw the, or write the torque vector if you need it.